Swayam Prabha. Digital India. Educated India.
Let's continue our discussion of axiomatic considerations in the context of voting mechanisms, and we are just at a point where we have realized that sometimes even fairly innocent looking requirements can land you in a bit of a soup. So in particular, we saw that asking for unanimity and independence of irrelevant alternatives actually leaves you only with the dictatorial voting rule, which I think most of us would agree is not a good situation to be in, but that is sort of the mathematical reality that we have to wrestle with. Do you have any suggestions for how to deal with this situation? We seem to have a result which tells us that there isn't a good voting mechanism. Very roughly translated. So at this point, since some of this is also, we decided that we wanted independence of irrelevant alternatives. All of this is up for debate. So are there any remarks or suggestions? So first of all, I'm not going back to the proof. Was there anything that requires a clarification, or if there were any questions, then we could discuss that as well. So even if all the details are not transparent, hopefully the overall idea is clear, which is to say that you find a pivotal voter for a particular candidate, use unanimity and IIA to derive certain properties of polarizing candidates, and we had that trick where we had a sequence of profiles which we used to identify the pivotal voter for a particular candidate. And then we said that this pivotal voter is in fact decisive for all pairs of candidates not involving the polarizing candidate. And finally, we had a short observation for why this also works for pairs of candidates involving the polarizing candidate. So those were sort of the steps in the proof. And I'm confident that if you go back and look at it once more, it will be reasonably clear. It turns out that this theorem has several different proofs which use several different approaches. If you're interested in a slightly different approach, you can also look at the handbook which we are referring to. You can find it in the references section of the website for the school. In the very first chapter, they introduce Arrow's theorem, and they have a slightly different approach where they essentially say that you can, if a collection of voters is decisive for a pair, which is to say that if all of these voters say that A over B, then a collection of voters is said to be decisive for a pair. If these voters say A over B, then the mechanism outputs A over B. So unanimity is basically saying that the entire cohort of voters is decisive, right? Because if the entire cohort of voters, everybody says A over B, then the mechanism outputs A over B. That is the unanimity principle. And dictatorship basically says that there is a single voter that is decisive for all pairs AB, right? That in fact we don't even need a non-trivial cohort, that a single voter is decisive. So the main lemma there is to say that if you give me a collection of voters that is decisive, I can split it into two smaller collections, at least one of which is decisive. That is really the key lemma that they prove. And once you have that, it is not hard to see that you can use unanimity to get a starting collection of voters, and then you keep splitting it into smaller and smaller pieces until you end up with one voter. So that is the approach there. It's slightly different, but it's also worth going through. It's a manageable proof. And if you look it up online, you will find several other approaches to this theorem. It really is fairly fundamental and has been revisited in several contexts. We won't really be getting into the various offshoots. It's kind of beyond the scope of this discussion. But there are two major reactions to a statement of this kind. The first natural reaction that a lot of people have is to say that independence of irrelevant alternatives is something that is rather strong, and that we shouldn't demand it. It's too much. The other thing is to go back to the setting of the theorem, which looks at ranked ballots, and you might say, well, our setting is social welfare functions, which takes a collection of rankings and outputs a ranking, and you might want to relax that and say that, well, what about other settings that are equally relevant but may have more reasonable outcomes in terms of admitting reasonable mechanisms. So those are the two things that immediately come to mind. Is there anything else that you would like to suggest? So, okay, the first thing that I said about debating the axiom, I'm going to not get into that very much, but in fact, independence of irrelevant alternatives has a nice Wikipedia page where there are lots of examples for a lot of otherwise reasonable voting rules that violate the axiom. So you can actually look at it, and you can also see a lot of references to critiques of the axiom. So if you're interested, that's some nice background reading that you can catch up on. So independence of irrelevant alternatives is debated, not only because it leads to this sort of an impossibility result, which is very stark, but also on its own right. I mean, not everybody agrees that that is something that we should necessarily demand, and that the role of a third voter can be critical when it comes to determining the ordering between two other alternatives. So that's it's more of a subjective discussion, and we are not going to go down that path right now. The other thing that one might ask is, well, for social welfare functions, yes, we are stuck in this mess. What about other sorts of mechanisms that aggregate preferences? So in particular, let's just consider what we said we will start with, which is, okay, I erased the wrong word, but so social choice functions. Again, there are two related notions. I mean, if you want to allow for ties, then you might want to output a subset of candidates. Okay, but we are going to be thinking about resolute voting rules, as they are called, which is basically that they take a call and output a single winner when they are given a collection of rankings. Yeah, so these are called social choice functions. So the output is a single candidate rather than a ranking, and frequently in many applications this is also what we are interested in. We want to elect a winner or a leader, or we want to figure out where we want to go for dinner. So this is not an unreasonable relaxation to consider, and let's investigate social choice functions for some time. So in this setting, things like unanimity and IIA don't really make sense in the way that we have stated them, because, okay, why do they not make sense in the way that we have defined them? So what would it mean for a social choice function to be unanimous? I mean, if you just read the definition out to yourself, you'll see that it doesn't type check, right? I mean, you are saying that the function must output A over B, but the function is not even giving you a ranking, so it doesn't make sense to talk about A over B. And it's the same problem with independence of irrelevant alternatives, right? So since we are not talking about rankings here, these are not the axioms that quite make sense. However, the mechanism of dictatorship can be naturally adapted to the single winner setting. So when would you say that a social choice function is a dictatorship? So one way of stating Arrow's theorem is to say that there is no social welfare function that simultaneously satisfies the following three properties. The first being unanimity, the second being IIA, and the third being the property of being non-dictatorial, meaning that the mechanism is not a dictatorship. So interpreting, so the first two properties don't carry over to the setting. The third property of being non-dictatorial can be reasonably adapted is what I'm suggesting. So what does it mean to be a dictatorship for a social choice function? Right. So you output the top choice of a fixed voter. So again, the philosophy is that you are, or the spirit of the definition is that you are always following what one voter is asking you to do. So there is a voter such that on all profiles, the choice of the winner is essentially the top choice of this voter. That is when you say that you have a dictatorship. Okay. So that is one property that we are certainly interested in. We want a mechanism which is not dictatorial. Let's go back to considering some other properties that we may want, right? So one property that may be reasonable to demand is the property of being onto. So what does it mean to say that a function is surjective? Or onto. You have seen this definition before, right? So what does it mean to say that a function is surjective? I'll just request somebody, some of the quieter ones, to maybe volunteer. What does it mean to say that a social choice function is onto? You already know what it means in general for a function to be onto. It just means that every element in the range has a pre-image in the function. So translated in the language of social choice functions, where the elements in the range are alternatives and the elements in the domain are profiles, how would you state this property? So all I'm asking for is a natural language way of talking about what it means for a social choice function to be onto. Is the question clear? Right. So the range of the function has size n, but that's still a fairly technical way of putting it. What does it mean intuitively in the context of voting? All of them have to appear once. Okay, so every candidate does appear in every ranking in every profile, because we have assumed that the profile consists of n linear orders, and linear orders are essentially complete rankings over all the candidates. So that we don't even have to request for this explicitly, because that anyway happens. Every candidate appears in every ranking. They may not appear at the top spot, for example, or yeah, but they do appear. But what we are saying here is that, as you said, the range of the function is n. What does that mean? So okay, let's just write out what it means for a function to be onto. So we say for every element in the range of the function, there exists an element in the domain of the function such that, so let me just say for every element in the range, there is an element in the domain such that the function maps y to x. Sorry? Right, okay, so range is already defined as, so that's a good point, thanks. So we just say, so the way I wrote it, I mean, if you think of the range as just being the image of f, which is how it is usually defined, the previous definition was a tautology and kind of trivial. So everything in the codomain has a pre-image. So the range is the codomain. That's what we want to say, right? Okay. So yeah, thanks for pointing that out. So for us, what is the codomain of the function? So we are looking at f, which is a social choice function. So the codomain is alternatives. And the domain is, what is the domain? Permutations of candidates, yeah, so a collection of n permutations of the candidates, which we would typically call a profile. So that's a voting profile. It's a collection of rankings over the candidates. So if you just read this out again, this just says that for every alternative there is a profile in which it is winning, because for f of y to be equal to x translates as x is a winner in the profile y. I mean, of course, as declared by f. And f says that x wins in this profile. So to say that a social choice function is onto is to simply say that every candidate has a chance of winning. I mean, this is how I would put it informally. Every candidate has a shot at winning. Is this a reasonable property to demand from a social choice function? Yeah. I mean, if a social choice function didn't satisfy this property, then there is some candidate for whom this is a completely meaningless game, right? They would not be invested in participating at all if they knew that there was absolutely no scenario in which they would emerge as the winner. And as rational people, we play to win. So if the mechanism itself is not giving you a chance, then that seems quite unfair, right? Okay. So onto is reasonable. I mean, we are not even demanding very much. We are not saying that every candidate has a substantial chance of winning or a decent chance of winning. Just saying that it has some chance of winning, some non-zero chance. It could be very slim, but so it's in fact a pretty weak demand, and I think therefore it is reasonable. So so we would like our mechanisms to be onto. Yesterday we spent some time talking about manipulation or cheating strategies. So I want to continue that discussion in the context of the axiomatic setting. So if you wanted to frame non-manipulability as a property, how would we do it? That also is something that seems like a reasonable ask. So this is called strategy proofness in the literature. This just means not being vulnerable to manipulative behavior. Yeah. So how do we formalize strategy proofness? What do you want to say here? So essentially, what is manipulation? In the way that we discussed it yesterday, we said that if it's possible for a voter to change their preference and obtain an outcome that works out better for them, then they have an incentive to actually report a fake preference, right? So if you change your preference and the outcome improves with respect to your true preference, then that would mean that you would actually be tempted to report a preference that's different from your truthful preference, right? So let's try to capture that. So we want to say that, well, since we are defining strategy proofness, maybe I should say that there does not exist any voter there does not exist a voter and let's say a pair of candidates for which what? So we want to avoid a situation where there is so there's a profile P where the mechanism F is giving us A. Let's just say there is a profile Q where the mechanism is giving us B, and what makes this situation capture the notion of manipulation? First of all, how are P and Q related? So I want to say that we want to avoid this scenario, right? To define strategy proofness, it should not be the case that there are two profiles P and Q, on one of which the mechanism outputs A and on the other the mechanism outputs B. When does this setting actually become a valid manipulation scenario? How do you want the two profiles to be related, first of all? Sorry? They are, okay, so I want to connect the profiles with respect to the voter I, because I'm thinking of I as the manipulative voter, right? So I want to say that these profiles are completely identical except for the vote of the voter I. Okay, so the ith voter may have a different ordering here. It would have a different ordering because if everything else is identical, then the outcome cannot change if something does not change. So, but nobody else has a different vote. Okay, everyone else is voting in the same way, but I has changed her preference. And how do we want A and B to be related? When does this constitute a valid manipulation? So for example, if in the true preference of I, B is ranked below A, would you consider this a manipulative scenario? If B is ranked below A, would the voter I be tempted to move to the profile Q from the profile P? Not really, right? However, if B is ranked above A in the truthful preference of the voter I, right, then the voter I looks at the profile Q and says that, okay, if I changed my vote according to what is specified in the profile Q, then the mechanism appears to give me something that I like more than the current outcome, right? So B is preferred over A in the truthful vote of the voter I. So I'm using the word truthful here in an intuitive sort of sense, What I mean is that in the vote that we have for voter I in the profile P, let's say that B is ranked ahead of A, which is to say that B is preferred over A. And in the profile P, the voter I sees that the output of the mechanism is the candidate A. And if the voter happens to be aware of the profile Q, where she knows that everything else is the same, all she has to do is change her vote to I prime, and that will compel the mechanism to output B, which is a different outcome that is preferred over the current outcome, then certainly we have created a scenario where there is temptation for the voter I to deviate from her current preference. Does that make sense? Yeah? Okay. So I am not writing this anymore formally. You would have to say there exist profiles P and Q, which are the same except for the vote of the voter I, where the output of the mechanism is A on the first profile and B on the second, and the voter I prefers B to A. So this is the property of strategy proofness. So are these two properties clear? The property of being onto and the property of being strategy proof. Yeah, you don't create manipulative scenarios and you give everyone a chance to win. That again seems like a perfectly reasonable set of properties to expect. And again, let me make sure that this. So by the way, we have seen examples of violations of strategy proofness already. We have seen that, of course, with plurality, it's not strictly vulnerable to manipulation because you really can't do much with it except for getting your candidate to tie. So there the tie breaking rule becomes kind of crucial. So it is mildly vulnerable to manipulation. But we've seen that rules like Copeland at least can be manipulated. You can convince yourself that Boda can be manipulated and so on. But all of these rules are onto, meaning you can construct profiles where any particular candidate comes out on the top, right? Okay. Can you quickly think about if dictatorship is strategy proof and if dictatorship is onto? So make sure I get this. Okay, so if you've been reading, this is our second depressing result of the day. But before we parse this, can we just quickly sanity check that dictatorships are in fact strategy proof and onto? So why is a dictatorship onto? So let's say that you have a dictatorship where the first voter is a dictator and you have a candidate A. What is a profile where A emerges as a winner? Right, so any profile in which the first voter places A on the top, A emerges as a winner. So get the first voter to place A on the top and complete the rest of the profile in any way that you like. In all of these profiles, A will turn out to be the winner under the dictatorship rule. So in fact, there are many profiles in which A is winning. So that would be on to. What about strategy proofness? Does any voter have an incentive to deviate from their truthful preference? So what about the non-dictatorial voters? Do they have an incentive to deviate? If the mechanism is a dictatorship with the first voter being the dictator and you are not the first voter, then anything that you do is not going to influence the outcome of the election, right? So if you are not the first voter, then this situation will simply not arise. So what F was spewing out here was the top preference of the first voter, and in the profile Q, since no other vote has changed, in particular the first voter's vote has also not changed, so that outcome will continue to be A no matter how drastically you change your preferences. Okay. So other than trying to persuade the first voter or bribe the first voter, you cannot manipulate in the usual sense of manipulation. Right? Changing your voter will not make any difference. What about the dictatorial voter? Does she have an incentive to deviate from a truthful vote? Does the dictatorial voter have any reason to deviate from her truthful vote? No. Because the voting rule is anyway listening to her, so why should she throw a tantrum? It doesn't make any sense. So the dictatorial voter also has no reason to deviate. So a dictatorship is indeed strategy proof and onto. And if you have again at least 3 candidates, then this turns out to be the only mechanism that enjoys these 2 properties. Okay, so again it's fairly stark, and I think in this context we will have a slightly more elaborate discussion of what are the ways in which we can sort of deal with this situation. But before we do that, I think I want to again spend some time conveying some intuition about what is going on here, just like we did for IIA and unanimity. So again, we are wrestling with specific properties here, and let's see if we can at least make a few observations. And what I'll try and do is give you an illustration for why something like this may be true when there are only 2 voters, and I'll leave it as an exercise in induction to see that you can take whatever we have learned for 2 voters and then expand it out to a setting with more voters. Okay. So the monotonicity property basically says that if you have a profile, okay, where F is giving you the candidate A and the mechanism F is, so throughout we will assume that we are dealing with a strategy proof and onto mechanism because that's what we are interested in, right? So we want to look at the class of strategy proof and onto mechanisms and basically just like before say shrink that class to the dictatorships. We want to say that there is nothing else that can manage. So if F is strategy proof and onto, then if you go from a profile P to a profile Q where A's position either stays the same or improves for any voter, okay. So A is winning currently and A only gets promoted or stays the same in the new profile, then A continues to win, okay. That's what we want to say. So Yeah, so this is called monotonicity. And again, I'm going to pause here for a minute or two to allow for parsing. So is the claim clear? If everyone either keeps A at the same position, so A is the current winner with respect to the profile P, and if everyone either stays, keeps A at the same rank or improves the rank of A, then A should not be dethroned as the winner. That seems like a very natural thing to expect. But again, you can think of examples of mechanisms where this may not be true if these assumptions do not hold. So we are saying that the mechanism, we are implicitly assuming that the mechanism is onto and strategy proof. I mean, I have not written it out, but that's what we have.